when all the source words are translated, we got the target sentence. So we can see there are many steps in this process. At each step, we have a lot of choices. We can, for example, for the first word, we can select the first word in the source side or the second word or any word in the source side. And given the word in the phrase table, maybe there for the same source phrase, there are many different target phrases in the phrase table. So at each step, there are a lot of choices. So in this way, we can see the decoding process can be understood as a search program, a search process. So we try to search translation, the best translation for the source sentence. So in the search process, we rank all the candidates by a statistical model, by probabilistic model. So this model is defined in statistical machine translation. Okay, that's the basic idea of statistical machine translation. For deep learning, I understand most of you are familiar with this technique, so I will just skip these slides. So then I try to explain the gap between deep learning and the machine translation. So machine translation is a task to transform a sentence to another sentence. Each sentence is represented by a sequence of words. So we can say that the translation task itself is defined in a discrete space. So in this space, every word are discrete symbols. So there are no direct connection between these words in this space. But in deep learning, a neural network is a function defined in a continuous space. So everything is represented as vectors. So if we try to use deep learning to implement a machine translation system, first we need to convert the task, the empty task, from a discrete space to a continuous space. So that's the idea to do the transition. We need a transition from discrete spaces to continuous spaces. So first we need to map each word in the source side to a continuous space. So this technique is called word embedding. So that's the idea. So we can see in the left side we have a discrete space. There are many words there, but we need to map it into a continuous space. So just to map each word to a vector. The simplest idea, the most straightforward idea to do this is use one-hot vector. So the one-hot vector, the dimensions of this one-hot vector is exactly the vocabulary size. So in this vector, we use each dimension to represent a word in the vocabulary. So each word is represented in a one-hot vector. That means only the dimension which is correspondent to this word is active, is equal to 1. All the other dimensions, all the other elements are inactive. So this is called one-hot vector. But the one-hot vector is not good. It's not good for computing. So because the dimension is too high, so usually you see the vocabulary size usually maybe several tens of Ks or 100,000. So the more important is very little information is carried by a one-hot vector. So in the one-hot vector, we have no syntactic information, no semantic information. So that's not good for computing. To solve this problem, so there are some different ideas. So before we have deep learning in NLP, we use another technique called distributed semantic models. So the assumption is the word that are occurred in the same context. So we try to use the context information to represent a word. So the typical model is called a context window model. So in this idea is we still use the long vector which has the same dimension of the vocabulary size, but we just sum, or we use the sum or average or TF-IDF of the one-hot vectors of the surrounding words to represent the current words. So this idea is very good. So it's very effective for computing the word similarity. Also, we can use some other technique to reduce the dimension, to greatly reduce the dimension, but it's still not good enough to implement a machine translation system. The reason is, first, it's not compositional, so we cannot derive the properties of a phrase from its word, the words in the phrases. And also, we cannot do the reverse mapping from a continuous space to the discrete words. That means we cannot implement the machine translation purely inside a continuous space. We cannot get rid of the words. So that is not purely we cannot implement the machine translation purely in the continuous space. So in the deep learning framework, we represent words to the vectors in another way. So we call this technique word embedding. So the most popular technique for word embedding is word-to-vec. So the idea of word embedding is we first defined a matrix for word embedding. In this matrix, each row is a vector, represent a vector for a single word. So you can see this example. Here we can see the king. This row have a representation of have the is correspondent to a vector. So this vector is just the word embedding for this word, the word king. So this matrix can be initialized randomly, and then we use neural network to train this vector, to train this matrix. So the idea is there are two different models. So one is called CBLW. This is the other is skipgram. So the idea is for CBL is to use the surrounding word to predict the current word. So we define a neural network here. The input is the context of the current word. Output is the current word. So we use this model to repeatedly train to adjust because we given a monolingual corpus, we can got a huge number of instances to train this model. So the skipgram is trained model in the similar, but it uses the current word to predict the content word. So by use this kind of technologies, we can obtain very good word embeddings. That means we implement the mapping for a single word from a discrete space to a continuous space, and then next we need to express a sentence, not only a single word, to a continuous space. So the idea is use a neural language model. So before we introduce neural language model, we introduce the idea of language model first, the general language model. So the language model is used to give a probability of a single sentence in a language. So that means here a typical language model is implemented this way. So we just need to estimate the probability of each word given the history of the sentence. So if the word 1 to word I-1, we just predict the probability of WI. So the traditional, the most popular language model before we use neural network this n-gram language model. In this case, we use a Markov chain assumption. That means each word is just the probability of each word is just depending on limited history of this word. So here is an example of the bigram. So in this case, we can see, given the previous word, we can estimate the probability of the current word. So that means, for example, the previous word is I. All the probability of the current word is represented in this row. So we can see there should be a normalization in this row. So all the probability in this row should be summed to 1. So in deep learning, we can re-implement a similar language model, use feed-forward neural network. So this is an example of this feed-forward neural network. This is very similar, but we don't use the n-gram ID technique. We use n-gram language model technique. We use this neural network. So the input is the previous n-1 word, and the output is the current word. So this is the same. So we use input of the previous word, and we use neural network. So the important thing is here is for the output. So we have a soft masked layer. That means in this layer we have the n word. The n is equal to the size of the vocabulary. That means each neuron in this layer represent one word. So by this, we can by this feed-forward neural network, we can got a weight for each word, and finally we need to do soft marks. We do normalization on the whole vocabulary size. So this is computational intensive. You can see. So one shortcoming of this feed-forward neural network language model is that it can only take limited history, limited length of the history. It's just like n-gram model. So an improved version of the neural network language model is to use the recurrent neural network. So maybe you should familiar with the recurrent neural network. This is a neuron for a recurrent neural network. The idea is we use a content to represent the content vector to represent the state at each step. So we use the previous context as the input and the current word as the input to calculate the distribution of the output in the whole vocabulary. So here is the unfold. The figure give you the unfold RNN language model along the timeline. So at each time, you can see we accept the previous state as the input and the current word as the input, and then we can generate a distribution in the vocabulary size of the output word. And also we have you can update the current state, and we output the opposite the state to the next step. So by this, we not only can calculate a probability of each sentence, but also we have a vector to represent the whole sequence. So this is by this way, by neural network, we not only got a probability of each sentence, we also have a representation of the whole sentence. So we call this an encoding. This is a kind of encoding. So the simple RNN is not good enough. So it has the problem of gradient vanishing and the gradient exploding. So there are other versions of RNN proposed to solve this problem. So the most popular new RNN is long short-term memory and gated recurrent unit. So language model cannot, the neural language model can not only be used to encode, but also we can use it for text language generation. So here, with the graph, we can it show how to generate a sentence. So given a start point, given a start state, we can generate a state, and we can have a distribution on the vocabulary of the output word, and then we can select an output word, and we can input this output word to the next state and also the current state, and we generate the next state of the next word and output the next word. So by this way, we can generate a sentence. So we can see neural language model can not only be used for encoding, but also can be used for decoding. So we almost have the idea of statistical machine translation. Okay. For neural machine translation. So neural machine translation is try to implement a machine translation in the continuous space. That means we can see that we can understand a source sentence is a path in the source space, continuous space for the source language. And given this path in the source space, we try to generate a sentence in the target side. That means we try to find another path in target side in the target space. So first we'll introduce the basic idea of neural machine translation, and then we'll introduce the most popular attention-based neural machine translation. So we almost have the idea. So we use a neural language model to do encoding, to encode the source sentence to a vector, and we use this vector to generate a sentence in the target side. So that's the idea of neural machine translation. It's quite simple and straightforward if you have the idea of neural language model. So this figure shows the process of neural machine translation. So actually, you can see in the bottom, we have a neural language model. It's a RNN model for encoding. We can got a state here, and we use this to generate as a language model. We use the language model reversely to generate a sentence in the target side. So the idea is quite straightforward if you have the idea of neural language model. But it is not good enough. Actually, this simple neural language model did not outperform the traditional statistical model, because you can see the weakness here. The problem is, the only connection between the source sentence and the target sentence is the single vector, which represent the source sentence. But the sentence may be very long, so it is hard for this fixed length vector to capture the information of the whole sentence, especially when the sentence is very long. So when the sentence becomes longer, the translation quality drops dramatically in this model. So the improvement of the improved idea is we use attention mechanism to improve neural machine translation. So there are several ideas for attention-based model. So first, we keep the state for all the words rather than the final state only. We have a separated state for each word in the source side, and then we use a bidirectional RNN to replace the only single directional RNN. Finally, we use attention mechanism as a soft alignment between the source words and the target words. So this figure shows the idea of bidirectional RNN. You can see here is a forward this is a forward RNN, this is a backward RNN, and we keep the state at each step. So at each step, we have a content vector for this word, and we concatenate the state in the forward RNN and the backward RNN to represent the state of the word, the context of the word. So we can see this state contains the context of information from both sides, from left side and the right side. And then we need to use another mechanism which is very important. We call attention. It is an attention mechanism. So the idea is not in a simple language model for generation. We have for this at each state, at these neurons, we have the input from the previous state and the previous word. Here we also include another input from the source side. So this input is a weighted sum of the state of each source word. So this provides a soft alignment between the source word and the target word. That means for this word, it is strongly connected to some of the source word, but weakly connected to other source word. So we have a weight between the state of this. We have a weight between the target word and the source word. So how to calculate the weight? So for calculate the weight, we use another simple feed-forward neural network, which takes the input from the previous state and the current, the state, the context vector of the source word. So by this neural network, we can calculate a weight for each source word. Okay, so then we can calculate the sum, the weighted sum of the source word, and get a representation for the source sentence, especially defined for this word, for this target word. So by this, we got a soft alignment between the source sentence and the target sentence. So attention-based neural machine translation is very powerful. So it is the first time for a neural machine translation outperform the state of art of the statistical machine translation. Okay, then Peyman will introduce the implementation of a sequence-to-sequence model with PyTorch.
So, okay, thanks to Professor Liu. He explained the neural machine translation with a fair amount of details, so we are good to go. And now we can implement a neural model, like sequence-to-sequence model with PyTorch. I've worked with Theano and TensorFlow, but this is like personal idea. But if you want to implement the same model with one of these frameworks, probably it will take a couple of hours. But PyTorch is like very straightforward, very well developed, thanks to the developers. I would say that it's a very elegant framework to play with. So if you are not a PyTorch user, give it a try. It's very straightforward and handy. Sorry. So I'm going to talk about almost the same things, but not from the theory perspective. So I'm going to give some implementation tricks and some hints about the encoder-decoder model. But I need these slides. I need these fundamental explanations. So whatever, if I'm boring you, sorry. But whatever I'm explaining here, I'm going to use in my next slide. So we know that encoder-decoder model is just a simple connection of two RNNs. The first RNN is responsible to encode the source sentence, and the second RNN is responsible to decode, like get the source sentence representation and sample one word at each time step. So they work together and they are trained jointly. But if I want to unroll and unfold this recurrent structure here, we would have something like this. So at each time step, one word comes in, and this is one embedding for the cat, let's say. and we have to update our hidden state. Along with the hidden state, we have some other concept which is called context, and we've already mentioned what this context is. So this is what happens in reality and in practice. We also have almost the same structure in our brain. So we have to update our hidden state and also the context vector, because we want to know about the significance and the importance of source words. So yeah, if we unfold the structure, as I mentioned, the second word comes in, the third word, you can consider this one as a one loop here. So this is one layer recurrent neural network, and we have loop. And if we unfold this loop, we have this structure here. The one, second, third, fourth, fifth words comes in, we update our hidden state and also context. And after visiting the EOS, or end of sequence, we are almost done, and we did the one phase or one path of our encoding process. Then we switch to the decoding process. We initialize our decoder with the context vector, and each time step we start to sample or generate one word at each time step. We generate the first, second, third, fourth, and the last word. The last token is EOS. EOS is like a signal to our decoder and says that, okay, stop, we generated the full sentence, then we have to jump to the next step and do the other iteration for the other instance in our training set. So in our training set, we have the structure of our training set is like this. We have a pair of sentences. The first one is the source sentence. The second one is the target sentence or the translation of source one. And this whole thing here is one instance in our training set. So, and we have very important concept here, which is called attention. And the attention shows the importance or significance of each word on the source side. Given the state of the decoder, this keyword state is very important for me, and I'm gonna talk about these things. Basically, I'm gonna implement this state word. So it is very important. Given the state, we try to extract or find the most relevant words for translation. Let's say this is not just a simple example. This is one example from my training set. And when I'm translating this green word here from English to Farsi or Persian, when I'm translating this green thing, if I visualize the intensity of colors shows the impact of each attention weight. If I visualize my attention weights, you can see that, for example, alpha 6 is 0, or the impact of EOS is nothing, almost nothing. Or alpha 1, the cat, the word cat here, has a very tiny or negligible impact on translating this. But these three vectors here, or these three words here, are very important. So because of that, we have high intensity colors here. So, but this is our interpretation from the attention mechanism. Basically, we think that we are doing search things here, but what happens in practice is a very simple thing here. We have different hidden states here from our source side. We want to find the vector of weights. Basically, it's like one vector level product or multiplication and one vector level summation. So attention mechanism is not something complex. We have one product here and one summation here, then we generate the context vector. After finding these, which neural network is responsible to find these weights? After finding these weights, we basically multiply this alpha 6 to EOS, and we have the new vector here. So you can see that, as I mentioned, the impact of EOS is 0. So alpha 1 is 0, alpha 6 is 0. If we multiply alpha 6 by EOS, we would have this thing here, which basically we are kind of excluding the impact of EOS here. If we sum these things up here, we have the new context vector. So context is one vector, one-dimensional vector. And if you look at the content of this context vector here, we have some red things here, which shows the impact of these words here. Also, a dominant part of the context vector belongs to these green things, which shows that these words are very important. And also, we have some gray things here, which shows the impact of these things. So the context vector is a weighted summation, is a dynamic structure, which is defined based on the time steps and the state of the decoder. So this is the theory or fundamental information about the neural networks. And let's just dive into our codes and let's see if we can implement a neural model with PyTorch. So encoder, first we have to encode our source sentence. And as I mentioned, encoder is a simple recurrent neural network. So we define one class for our encoder, but in PyTorch, whatever you want to work with, and the main module and the main class in PyTorch for neural networks is this one, is nn.module. So what structure you define, you have to inherit from this superclass here. So basically RNN encoder is RNN, and we have to inherit from this nn.module. Then we initialize our model. This first parameter shows the number of source words. Let's say we are translating from English, and in English we have 50K or 50,000 unique words. So input on this input shows the number of unique words. And also we have hidden size here. If you look at here, we have hidden state, and the dimension or the size of this hidden state should be defined, which the second parameter here shows the size or dimension of our hidden state. And we have very important things here. This keyword has nothing to do with deep learning or PyTorch. This is a Python thing. And the best explanation for this keyword you can find here. But as a simple explanation, let's say you have class A, and the class is inherited from B, and B is inherited from C, and C is inherited from D and E or other classes. If you want to have the behavior or the features of all those superclasses in your A class, you can use this keyword. If you have this super here, it means that you are getting the benefit of all superclasses, and that's the simple explanation for this keyword here. But if you want to know more about this, I think this link provides the best example for this. Then we initialize it, and we define our embedding table. As Qun mentioned, each word is represented with the one-dimensional vector or one embedding, and we need the table to store and to save these embeddings for our encoder. So this structure is defined by nn.embedding. The main feature about this table, basically nn.embedding provides one table, but the main feature about this table is that this table is dynamic. Basically, we are treating each cell of this table as a weight, and this table is a weight matrix, and we're updating the weights during training. So we at each iteration, we touch every single cell here in our table, and we update the content of this table. So the structure of this table is like this. This dimension shows the number of unique words, and this dimension shows the embedding size for us. For example, look at this red line here. Maybe this is the fifth, I don't know, sixth, seventh row of the embedding table, and it shows the, for example, embedding of cat for us. So each row represents one word for us. Then I'm going to explain this GRU in the forward pass. In our neural network, you know that we have a forward pass and backward pass. In forward pass, we compute our results, or we generate our target. Then if the target is fine, if it's correct, then that's perfect. Otherwise, we have error. We compute the error based on our loss function, and we backpropagate everything to our neural network. So we usually define forward classes or forward pass in our RNNs, and we define the backward pass in our training class. So basically, now I'm going to explain the forward pass, and for the backward pass for computing the gradients and updating our modules. So I'm going to talk about these things in a different class. So we feed our neural network with this input here, and this input is a digit. So basically, we send one digit or one index to our embedding table, and it extracts the word embedding for us. Let's say the index for cat, we are at the beginning. We want to encode our sentence, and the index for cat is 5. So we send 5 to our RNN, and it extracts the 5th row of our embedding table. And I'm going to give an example for this view here. This view, using this view, we make sure that we have the right dimension for our RNN. So the input of our RNN should be one element, that the dimension of that element is 1 times -1. -1 in PyTorch means basically we don't care about the dimension. The third dimension would be 100, 1000, or whatever. But the second dimension would be 1. So basically, we need one vector here. 1 times -1 means vector, and this one shows the number of that vector. We extract that embedding here. We then send that embedding to our GRU. GRU is a memory augmented RNN, but the basic and the most important function that happens within GRU is like this. So you have your embedding here, then you have your previous hidden state, you combine them and you generate the hidden state, and this hidden state generates the output. So you can show this structure with this picture here or this one here, but basically they are the same things. And as I mentioned, GRU is like a simple RNN you can consider as a one layer recurrent neural network here. And also we have one class for initializing our neural network. At the beginning, like our RNN is empty, and we have to initialize it, which the best way for initializing our hidden state is filling that with zeros. So we define this class for filling our RNN with zeros. So this simple, we are done with our encoder, then the decoding time. But in our decoder is not that simple, because we have to do decoding and also attention at the same time. So we have a bit complicated structure in our decoder. Almost the same thing here. We define our class, we initialize things, and we also have dropouts. You know that we use dropout for reducing overfitting. In my implementation, I always use dropouts. So it is better to, after extracting the first step or the first output of our decoder, it's better to apply the dropout thing than send to the other steps. This is simple here, and this max length shows the length of, or basically it shows the number of our words in our sentence. For padding purposes or for excluding very long sentences, it is better to have this parameter here, but this is not a must, it's kind of optional. So this max length shows the number of words in our sequence, and we're gonna work with this length in our next slides. This is simple here. We basically initialize, this is a simple assignment here. Then we have another embedding table. But if you remember, we defined embedding table for us in our RNN, in our encoder RNN. But now we have another embedding table. So what's the difference between these things? The first embedding table is responsible to store and update source side words, but this one belongs to the target side. Basically, in this embedding table, we have Farsi, Persian, or Russian words if we are translating into one of these languages. And in the first embedding table, we have words from our source side. So also the structure is the same, like this dimension is the number of unique words on the target side, and this dimension is the size of our embedding. Then this red box, I'm going to use this red box in the next function. So line by line, I'll explain what does these things mean for the decoder. We have another function, again, the forward pass here. The input, the similar structure here, the input for the forward path, the forward function is 1 digit. Again, this digit is sent to the embedding table to extract the related word here. And as I explained in the encoder part, the structure of this embedding should be like this. It should be 1 element. If you are doing batch processing, it should be 10, whatever. But in our case, it should be 1. And 1 element of something, and that something is 1 vector, 1 times minus 1. And this minus 1, as I mentioned, it means that this dimension could be 100, 1000, or whatever. We apply the dropout here. Then again, we need some. So that's the structure of embedding is like this. So the input should be in this dimension. But the structure of concatenation function, we have a concatenation function. We should only send 1 vector. So to extract the embedding and like to get rid of this dimension, we need to use the zeros index or the zeros element of this structure here. So if you look at this dimension I explained here, with embedding 0, we get rid of this first dimension and we extract this. Then we have the same similar thing for the hidden state, and we concatenate them. And the reason that we use the concatenation function, if you remember that, I said that in my first slides, I said that given the decoder's state, we extract the most related words for our translation purposes. So what is the decoder's state? If you combine the most information, the most useful information that we can get from decoder is this. So we are working on this word, which is shown with embedding 0, and also the current state of our decoder is this. So if we concatenate them, this can give us useful information. Basically, this information here can represent our decoder's state. So that's the reason we concatenate embedding 0 and hidden state here. Then we have attention function here. If you remember from this red box here, so the structure of the attention function is like this, and also we also get take the softmax of this attention function here. If we send the concatenation of embedding 0 and hidden 0 to our attention, it's like a linear function. It maps these two vectors, it combines these two vectors to max length, and max length shows, as I mentioned, shows the number of words in our sequence. And if we take the softmax of this whole structure here will provide this for us. If you remember my explanation from the attention mechanism here, as I mentioned, we need one vector. The size of vector shows the size of words here, and also each cell here is one number here. Basically, it shows the percentage or the probability, which shows the contribution of this word. So that's the reason we use softmax. We know that softmax is a scalar. It maps everything in the 0-1 range, and the reason that we use this 0-1 range, basically we need something like probability. We want to show that how impactful this embedding is, and we rate the impact of this embedding with this value between 0 and 1. So that's the reason we use softmax. So we get the state of our decoder. We map that state into one vector. The dimension of one vector is 1 times max length, and max length shows the number of words here. And we also kind of squash everything into the 0-1 range to show the impact of each unit in our decoder. As I mentioned, we have one matrix level product and one matrix level or vector level summation as the attention mechanism. So we did the product and the multiplication. So the rest is here. We extracted attention weights, which these things here, alpha 1 to alpha 6, are attention weights. Then we need to multiply these attention weights by these hidden states here, which is done with this BMM. BMM is a matrix level product function of torch, and the format of the input for these things should be like this. So now, as I mentioned here, we have 1 times max length, but the input for BMM should be like this. So we have 1, we use the unquiz function, and we transform this shape to this shape. So it's not something like scary. We are just setting the dimension to feed the BMM function. So we are done with our attention mechanism. We have this structure. We multiply this structure by our encoder outputs, and we extract the attention weights or the context vector here. So this attention applied, the result here has this dimension, 1 times the embedding size. And after that, we again concatenate this attention here with our embedding. And the reason is this: if you look at the original paper of the EncoderDecoder model, which was proposed by Cho in 2014, the output for the decoder is generated by this function. This is a screenshot from the original paper. So we feed the output function with the hidden state, with the current word, and also with context. So this C context is here, applied, the attention applied here. So this represents C here. And this YT-1 is here, which is our current word, which we are working on that word, and we want to generate the next word. And this HT-1 is the previous hidden state that we have it here. So the reason we are concatenating these things, because we want to generate this part of the function. We concatenate them, and we also need another mapper, or basically linear function, to change the dimension, because we know that the GRU, the dimension for the input of GRU would be something, and the output is defined at the beginning. So to make sure that we have that dimension here, we apply another nonlinear function. So we connect these things here, we concatenate them, then we change their dimension using this linear function. And after that, we apply nonlinearity, which is clear Y. And after that, we have our GRU. So if you look at this notation here, then function, GRU function is here, HT-1 is hidden here, and the combination of these things, like the attention, the information from the source side, all weights, and the reshaped and the reformed structure is here, is represented with output. So we send output and hidden to GRU, and we generate new hidden state and new output. Then after that, we take the soft log of our softmax of these outputs here. And the reason we take the softmax, again, we know that decoder is a classifier. At each time step, we want to hit the right word and extract or generate the right target side word. So, and because of that, we need some probabilistic values, and because of that, we take the softmax. And this log is because of the cost function. We use the log linear, negative log likelihood of the model. So because of that, we have to take the costs. We have to take the log and compute the log of our softmax. Then we generate these, we return these things, output, hidden, and the attention weights as the output of our decoder. Similar to our encoder, we also have a initialization function to fill everything with 0 at the very beginning time step of our decoder. Now we implemented our encoder, we implemented our decoder. It is time to put everything together and train our neural network. So we define new function here, which takes the encoder, decoder, and other initial values and initialize everything for us to do the training phase. We know that our RNN is a neural network, so basically we need to define an optimizer for our RNN, which is stochastic gradient descent. And we have the same structure for our decoder. So basically, we define our optimizers for encoder and decoder. Then we have our training pairs. If you remember, I mentioned that each training sample is something like this, is a tuple something like this, and each element of this pair is one sentence. This shows the source side or the source sentence, and it shows the target sentence. Then we define our cost function, which is negative log likelihood. That's the most basic and the most common thing for neural machine translation. But if you look at the literature, you can define your own cost function or some fancy things like based on BLEU or other optimization models for your neural network. But this is the most common thing that we use for our neural machine translation. Then we select these source and target sentences from each other and separately send them to our trainer to train our model, basically. And now we have another function here, which is responsible to compute loss, to generate the results and backpropagate everything to the neural network. First, we initialize our gradient values with 0 to make sure that we are doing the right computation and we are computing the gradient values for this path only, for this iteration only. Then this is the structure for our input and output. But to extract and compute the gradient of each thing, these structures are tensors here. But to make them derivable and to be able to extract the gradient of these things, we have to transform them into a variable form. So this is one class or one feature which is defined in PyTorch, and using this keyword here, you transform everything into one variable. And by the variable, as I mentioned, you have something that you have data and you have function in it, and you can get the gradient of that variable. Then we have this structure here. We send each sentence to our trainer. This trainer iterates over words, selects one word, and send the word to our encoder. Our encoder do the recurrent things here and generates the output for us. And also, if you remember this structure here, we mentioned that we need these hidden states for our decoder. Basically, we want to compute the attention over these hidden states, and because of them, now we are kind of storing and saving our hidden states here in this structure. And after that, yes, we are almost done. We send our data to our RNN. We compute the RNN results or encoder results. Then we store our hidden states. We send our hidden states here to our decoder. And now we want to generate the final output or the final word for our translation phase. You can do in different ways if you are using teacher forcing, or if you are not using teacher forcing. By the teacher forcing, I mean that if there is a direct connection between your output to your, like if you have one feedback directly from your output to the input of your hidden state, this mechanism is called teacher forcing. This is clear here, and I put comment here to show the difference. But if you want to use your own prediction as the input for your hidden state, you can switch to this part. So basically, if you use the direct output of your RNN, you are doing teacher forcing. Otherwise, if you are using your prediction to feed your RNN, you are doing this block here. And after that, we send this decoder output and our predicted output to this criterion function, which is a negative likelihood, and we compute the loss. And after that, we backpropagate everything to our neural network. In our backprop phase, we touch every single node in our neural network to update our weights and parameters, basically. That you can do this backprop phase with loss.backward. This is the function which is defined for that purposes. And as I mentioned, at each step, we have to update our weights, which is done with this. So encoder optimizer step means that one step of iteration, one step of backward pass, and it means that update our weights with this new value. Then yeah, we are done. We implemented our encoder, our decoder, we put them together, and we implement the whole sequence-to-sequence model. This is the main skeleton and the most basic code for our neural machine translation structure. But if you want to develop your fancy things like character-level neural machine translation, or if you want to use convolutional things, or if you want to have beam search in your generation time, you would basically use the same thing, but you need to add something on top of this. So that's the main skeleton for your neural network. So now Qun is going to conclude the presentation with his explanations.
Okay, thanks, Peyman, to give the introduction of the implementation. So let's conclude our presentation. So first we have introduced the machine translation. So machine translation is a task defined in the discrete space, but in the deep learning framework, we need to convert this task to a continuous space. So word embedding is used to map a word to a vector. So from a discrete space to a continuous space. So recurrent neural network is used to model the word sequence. So, and we use a encoder-decoder model or sequence-to-sequence model to implement neural machine translation. That actually we use a neural language model for encoding, and we use another neural language model in the target space reversely to generate the output sentence, to generate target sentence. Finally, we add attention-based mechanism to provide a soft alignment between the source sentence and the target sentence. So currently, the neural machine translation has outperformed the traditional statistical machine translation, and there are still huge potential for neural machine translation. So finally, I guess just give some further topics you can, if you have interest. So there are some good work on sub-word level or character level models for neural machine translation. That means the model is not built based on word, it's based on morphemes of the word or character. So this is very useful and important technique for neural machine translation, actually especially in real use. So it can be used to tackle the problem of morphologically rich languages, and also to solve the problem of out of vocabulary problem. Then there is also multitask and multi-way models for machine translation. So using these models, we can share parameters among multiple neural machine translation models, and it will be very useful technique to solve the low resource language pairs or even zero short language pairs. Currently, there are some new models provided by Google. I call it pure attention models. You can refer to the paper attention is all you need from Google. So it provides much higher performance than the current the attention-based neural machine translation. So actually, this is the state of the art. Okay, that's all. So
yeah, so I'm gonna
switch back.
Yes, and if you have any questions, just give me a second. Yeah.
Okay, guys, let's first thank the speakers. And first of all, I have a very quick question. Do you have your EncoderDecoder model code available anywhere?
Actually, it depends on the framework. If you are working with piano, it's really organized. Can you hear me? I have.
Sorry, we could not hear you. Could you please repeat?
It's fine now.
Yeah, echo.
Yeah, I hear my voice back.
So maybe you need to move your microphone away from the speaker, from the your microphone is too close to the speaker, maybe.
You can hear me.
Okay, could you please try again?
Can you hear me now?
Just a little bit. We cannot hear you.
This is fine now.
Okay, could you try now?
Yeah. Can you hear me now? I think that's because of the mic. We are here to echo here.
Sorry, there are some technical problems. We are trying to resolve them. Could you please use headphones if it's possible?
we don't.
Yeah. Can you hear me?
Okay, now.
Try to reconnect.
Ничего не сделать? Можно попробовать сложить трубку и опять позвонить? Нельзя? Понятно. Okay, I think it's yeah. It looks like we cannot do anything here. Could you try just one last time?
Yeah, this is fine now.